is lecture 19 of the course on high performance computing. In lecture 18, let me just remind you, we had seen about exceptions, and exceptions are these hopefully rare events that occur but are important for not only for the operating system to share the resources of a computer system, but also for interaction with the outside world. So, there are two kinds of exceptions called traps and interrupts. In both cases, the handling of an exception requires hardware support, and therefore, I said that exceptions are essentially a hardware concept which must be utilized by the operating system, and the hardware must be designed to run through a series of events through which the operating system code can deal with the exception. That therefore, the exceptional situation need not be a problem as far as correct execution of programs are concerned, such as divide by 0, and further that the exception mechanism can be used to the benefit of the operating system in the sharing of the resources of the computer system among many programs in execution. Now, with this concept of the exception, we actually need to relook at our understanding of process lifetime. Now, you will recall that we had this perspective of process lifetime, that we could think about real elapsed or wall clock time, which is taking into account the entire history of events on a processor as far as use of the CPU is concerned, the different running processes at various intervals of time. Or we could look at the lifetime in which there was the virtual time, the virtual CPU time from the perspective of one of those processes, and that one could further look at the breakup of the intervals of time on the virtual timeline in terms of time spent in user mode and time spent in system mode. Exceptions raise an interesting additional question to worry about. Essentially, when an exception occurs, the handling of the exception is going to take some amount of time, because operating system code is going to have to be executed to handle the exception. And therefore, the time spent in handling the exception, in executing the exception handler, must be accounted against one or the other process. It could be that user processes P1 through P100 are currently on the computer system, and this is basically a question which we do need to know something about, because this may, depending on how this question is answered, we may have to be a little careful in using CPU virtual time as an indication of how much time our program is taking. So, let me just go into the nature of the answer to this question on typical systems, and then suggest what the ramifications are. So, the question is this: which process, when an exception occurs and the exception handler has to be executed, exception handler is part of the operating system, then which process has the exception handling time accounted against it? Now, the answer is that at the time that the exception occurred, the instant in time that the exception occurred, one of the processes, let us say P1, would have been the running process, and it is against process P1 that the time for handling the exception handler is typically accounted. Now, this means that all the interrupt handling time and trap handling time which occurs while the process is in the running state is accounted against it. Now, you should bear in mind that this is a little bit of an unfair accounting, because not all of the exceptions that occur when a process is running are actually the fault of the process. For example, we saw that if I looked at the, let us say, process P1 virtual timeline, and process P1 is running for first got 1 second, then gets another second, I know that once every, let us say, millisecond, a timer interrupt occurs, and the timer interrupt handler may take a few microseconds to execute or less, but all of that time is going to get accounted against process P1 as time spent executing in, not in user mode, but as time spent executing in system mode. Why is it accounted against system mode? Because whenever an exception occurs, control gets transferred to the operating system timer interrupt handler in this case, and conceivably if there is a large amount of time spent in that way, it will get accounted against process P1. Clearly, the timer interrupts are no fault of process P1. Similarly, when process P1 is executing and there are other users logged into the same system, and let me just back up a little bit. While it is correct to say that the timer interrupts are not due to process P1's execution, it is also fair to say that process P1, like all the processes, must pay the overhead of supporting the operating system, and that therefore the timer interrupt handlers should not be a problem with any process. They are essential for the correct running of the system. But let's look at another example. Suppose on the computer system where this timeline is being drawn, there are several users logged in, and one of the users is typing something at the keyboard. Now what does that mean? That means that when process P1 is running in this interval of time, whenever a keyboard interrupt happens, the keyboard interrupt handler has to be executed, and that interval of time too would get accounted against process P1 as time spent executing in system mode. Now the time spent in handling the keyboard interrupt generated by another user has nothing to do with process P1, and therefore one might say that this is an unfair accounting. Now one should also bear in mind that it's likely that these pieces of code are going to be written so that they are very small and efficient, the interrupt handlers and the exception handlers in general, and that therefore the amount of time spent in handling them may not be very high. But if there is a very high load on a system, in other words a large number of users doing a lot of activity, say a lot of typing, a lot of mouse movement, etc., then the amount of time spent in this activity could end up being non-trivial. So it is something that one has to be aware of, and I will raise this issue once again when we come up against it. But we should note that as part of the component of time that is reported back to a process, if it asks of the operating system how much CPU time was spent, was I running, then part of the time spent running in system mode could well be time spent handling exceptions, some of which may be interrupts that had really nothing to do with the process in question, and that's maybe a fact of life on the system that you're dealing with. Okay, now I'm going to switch from talking about the operating system side of process management to in fact the programmer side of process management, and this is a topic which I will title as concurrent programming, and it's essentially a new perspective on programming which may arise now that we know that we could write programs which run as multiple processes. Now let me just remind you that until now in this course, whenever we talked about program execution, for the most part we were talking about a program in which there was one flow of control. And what I mean by that is, if I looked at the program as, let's say, just its text, then one flow of control means that the program execution starts at some point, then it goes to the next instruction, then it goes to next instruction, then maybe there's a control transfer, it goes to a function call, it executes the function call, then maybe it transfers control back. And I could think of the execution of a process within this particular program in terms of this worm which is worming its way through the instructions of the program. It changes its direction whenever there's a control transfer and so on, but there's only one worm going through the text of the program. In other words, we were for the most part talking about one flow of control through the program. Now that we know about the fork system call, and we realize that operating systems support multiple processes, many of which could even be from the same program, this raises the possibility for us to write programs which are concurrent programs, or programs in which there is more than one flow of control. In other words, going back to a diagram, I could write a program which starts as one of those worms, flows of control, but at that point in time it might do a fork so that the parent flow of control continues, but a child flow of control starts. And from this point in time onwards, there are two flows of control, or two worms, working their way through this concurrent program. So that's going to require possibly a new perspective on what it means to write a program, with the understanding that there could be multiple processes which come into existence as a result of the execution of that program. So in a brief aside, we will try to understand some of the important concepts related to concurrent programming. So we are still talking about operating system related issues. We are still talking about issues relating to the way that the operating system manages processes, but we're just trying to see whether there's something that we need to know from the programming side in order to leverage or get better benefit out of this knowledge. So we'll briefly look at what concurrent programming might involve. Okay, so from what we've learned now, we understand that a concurrent program might be one way to set up a concurrent program. In other words, a program which has multiple flows of control might be to set it up as a program that runs as multiple processes cooperating to achieve a common goal. In general, whenever we wrote a program, the objective of writing the program was to achieve a goal. We always talked about, I defined a program as algorithms and data structures which were put together in order to achieve some objective, an objective. We are now in situations where we're going to have a program that runs as multiple processes, and they must be trying to achieve that same or some objective. But since there are multiple processes, we'll talk about how all of those processes cooperate, and rather than talking about the objective, we'll talk about that as their common goal. So there's this notion of cooperation which enters the picture. Until now, when we were writing our ordinary programs which had a single flow of control, there wasn't really a notion of cooperation since we were managing only one control flow. Now we are talking about programs in which there are multiple control flows, possibly multiple processes, and we do have to worry about how these processes could cooperate. Now, in some sense, one could start by saying that in order to cooperate, the processes must somehow communicate. And you could actually think about this problem in the more general setting of how do human beings cooperate. Is it possible for two human beings to cooperate with each other if they do not communicate with each other? And the answer is it may be possible if the two human beings have a long history, they have cooperated with each other many times in the past, and therefore now they are in a situation where they don't have to communicate in order to cooperate. They know very well how they're supposed to cooperate. But one could argue that what is happening there is some kind of implicit communication. The situation that we're in over here is where there are processes which cannot have any kind of pre-existing knowledge gained by experience. Human beings can gain by experience. These processes, we suspect, cannot. They have to be programmed to do whatever they do. And therefore, this seems like a reasonable starting point. Processes must somehow communicate in order to cooperate. When human beings cooperate, they communicate in various forms. Some of you may cooperate with others by talking. Others may cooperate with others by passing notes to each other. If you're not in the same room, you might cooperate by talking on the telephone. You might cooperate by sending email to each other, and so on. These are all ideas which are related to communication. And we need to understand something about how processes can communicate before we can talk about what it means to do concurrent programming. So the immediate task is to talk about how processes can communicate. And this is often, the topic of how processes can communicate is often described as inter-process communication. Of course, the word inter is not really, you may wonder why it's there. You can actually scratch it out. We're talking about the communication between processes. There's little concept of communication inside a process anyway. And this is sometimes abbreviated as IPC, inter-process communication. We're going to look at various possible ways that processes could communicate with each other. And for the most part, the ways that we're going to look at are supported on the operating systems that we've been talking about directly. Now, the situation that we're in is, I have two processes, say process P1 and process P2. I know that they have their separate virtual address spaces. Therefore, it's not like one of them can write a variable which the other can read. So they cannot readily communicate in that way. So we have to think a little bit about how they could communicate in the absence of that kind of a facility. And one idea which might come to mind is, we know that the systems that we deal with support this concept of files, and that files are entities which, from what I have mentioned, seem to exist on a hard disk. And as long as a process can open a file and has sufficient privileges to do so, it can communicate with another process conceivably through that file. So this may be a good starting point, the idea that processes can communicate using files. So let me just give an example. Let's suppose there's a situation where I have two processes. They happen to be a parent process and a child process. In other words, when my program started running, there was one process. Subsequently, it did a fork system call, at which point I call it the parent process, and the newly created process is what I call the child process. And I want, for some reason, these two processes to communicate. Now, for them to communicate, it may be possible that in the particular situation that I'm in, I need one of them to be able to communicate a value to the other. So let's say that the parent process has computed the value 6, and it wants to communicate the value 6 to the child process. And the question then becomes, how can the parent process communicate the value 6 to the child process? And first idea is one could do this using files. So one possible way of doing this is outlined here. Now I'm going to set this up using two files, because it's conceivable that I want the parent to be able to send data to the child, and the child might have to send data to the parent. And rather than using one file for both, I'll use one file for the parent to write into and the child to read from, and the other file for the child to write into and the parent to read from. So before the parent process does the fork, it could create those two processes. I'm sorry, it could create those two files, one for it to write into, the other for the child to write into. Now, we've seen that when the fork system call occurs, the child inherits a lot of things from its parents, such as its text, its data, its stack, and its heap. It also, as it happens, inherits information about files from its parents. So, we'll learn more about file descriptors and file pointers later, but for the moment it's enough to understand that as part of the fork system call, the child will inherit enough information about the two files that its parent had created, so that subsequently the parent and the child can be written to communicate by using one of the files for the parent to write and the child to read, and the other for the child to write and the parent to read. So, the idea is there is process P1, which is the parent, process P2, which is the child, and there are two files, file 1 and file 2. So, after the forking, if the parent wants to communicate the value 6 to the child, it writes the value 6 in file 1. The child, in order to see what the parent has communicated with it, so the parent writes into file 1, the child reads from file 1. If in response the child wants to suppose the child was to calculate 6 multiplied by 6, it would do so, and to communicate that back to the parent, it would write 36 in the file P2, which the parent would read, and therefore communication could happen. So, all of the contents of file P1 will be things written by the parent, which can be read by the child, and all of the things in file P2 could be things written by the child to be read by the parent, and therefore they can communicate. So, this is possible, and the only problem with this kind of a mechanism is that it uses files, and we have seen that anything involving files may well involve something which is as slow as a hard disk, and therefore any one of these pieces of communication between the parent and the child is going to involve one write to the hard disk and one read from the hard disk, which we have seen could involve a large number of milliseconds, if not seconds. And therefore, one can understand why I have put this down as the first idea in interprocess communication, because there better be better ideas than this, since this is going to be a very high overhead way for one process to communicate with another process, in terms of the amount of time that it will take for a single value to be communicated from the parent to the child, conceivably several milliseconds, if not seconds, and that is an enormity of time on the time scale of the processor, right, as we have seen, several orders of magnitude. All right, so it is possible to set up programs so that processes communicate using files, but we want some better ideas, and one kind of an idea which is supported by almost all operating systems is the idea of something called a pipe. That's why I put it in blue, it's a technical term, and it turns out that the pipe looks superficially very much like the mechanism that we were using just now using files. In essence, what the pipe provides is two file descriptors. In other words, two mechanisms that could have been used to read and write into files, but rather than using them to read and write to files, it short circuits the mechanism, bypasses the disk, and directly does the communication through the operating system. Therefore, this mechanism will not involve the overheads of the hard disks, but will provide the same kind of facility for a parent to write into a file descriptor. Subsequently, the child can read from that file descriptor. Similarly, the child could use the second file descriptor to write, and the parent would read from that to communicate values one way and the other, without the disk being involved, without a hard disk being involved. Right? So, the general idea is there are two file descriptors which would be declared something like int fd2. So, the two file descriptors would be fd0 and fd1 as far as a pipe is concerned, and one could be used for reading and writing between the parent and the child, etc., along the lines of what we had seen for doing with the file. And the main difference is this will not involve the overheads of dealing with the file stored on a hard disk. So, this becomes a mechanism which would actually be feasible in terms of the time scale of a processor. It will involve system calls, it will involve some amount of time for the transfer of data, but will not involve the milliseconds of time we were worried about as far as the hard disk is concerned. So, this is some form of a rationalization in terms of overhead of the idea 1, but must be supported by the operating system. It must be provided as an operating system facility. Okay. Now, there are several other ideas. Now, one of them, strangely enough, is that processes could be made to communicate through variables that are shared between them. Now, I had explicitly said that this is unlikely to be the kind of thing that can be done, because because of the way that we have looked at processes up to now. But let's suppose for the moment that it is possible. So the idea here is that there will be some variables which can be used between process P1 and P2 for the purposes of communication, and we will refer to those variables as shared variables, and the variables of the process which are not shared we will refer to as private variables. Right? So it's possible that I have process P1 and process P2, and they may have one variable that is shared and all their other variables are not shared or are private. Now this is a bit of a oddity, but we could clearly understand that if this facility is there, then if process P1 wanted to communicate the value 6 to process P2, the program could be written so that process P1 writes 6 into that variable. In other words, it just sets x equal to 6, and process P2, in order to read the variable, would read x, and if it was supposed to square it, you can multiply x by x and put the value back in x, as a result of which x would become 36, which can then be read by the parent. So this will definitely be preferable to either of the previous ideas we have seen, which involved file descriptors, which may have been fairly may have involved a lot of system calls. Here we are clearly talking about something that might involve only memory accesses. Notice here there is no question of having to make a system call. The only problem that we have with this idea at all is because we have until now been talking about virtual memory, in which the objective of having virtual memory and address translation was to protect one process from another, and we were explicitly trying to make sure that one process could not access the variables of another process. Right? So we had set up things, our understanding was that the operating system set up things so that each process uses its own virtual addresses. So if there was process P1 and there was process P2, each had its own virtual address space, and the virtual address space went from 0 to 2 power n minus 1, and these were two virtual address spaces, and in reality there was physical memory, which was a physical address space, which went from 0 up to some 2 power m minus 1, and at any given point in time some of the contents, for example this page may have been over here and this page may be over here at some point in time during the execution of these programs. But our whole idea as far as virtual memory was concerned was to keep these two processes apart. Okay, now we are now told that it may be useful if the operating system can somehow provide support so that there is a shared variable. In other words, if the operating system could allow us to set things up so that this variable x is actually such that if it is in memory, the mapping for the page, suppose this is the page inside process P1 containing the variable x, and this is the page inside process P2 containing the variable x, is set up so that both of these pages map to the same physical address space. So in theory we understand that we wanted to keep processes separate as far as their ability to address variables of the other were concerned, but in practice, now that we've understood that a shared variable might be a useful mechanism for one process to communicate with another during concurrent programming, we see that it may not actually be that difficult for an operating system to help out. It basically just has to provide the mechanism by which, if I indicate in my program that the variable x is supposed to be shared between process P1 and process P2, then the operating system could conceivably set things up so that the page containing the variable x in the virtual address space of P1 and the page containing variable x in the virtual address space of P2 actually have the same mapping to a physical address page, in which case they will be talking about the same variable. And when process P1 writes into x and process P2 reads x, they will get the same value, and therefore they can communicate with each other just using ordinary memory operations by some kind of operating system support through the way that the mapping between physical addresses and virtual addresses is done. Right? So this can be supported by the operating system. The idea of shared variables, the idea that there could be variables which are shared between two processes, even though all the other variables and all the text and all the data and all the other stack and heap of these two processes may be distinct from each other in order to protect one process from the other. Okay? So this is something which can be done, processes communicating through variables that are shared between them, but it requires explicit support from the operating system. By default, the operating system's virtual memory management mechanisms are going to protect processes from each other, and therefore this would have to be some kind of a special mechanism which would be made available by specially declaring regions of memory as shared, through various kinds of system call mechanisms. So let us assume that this is possible, and on the systems that we are dealing with, we could find out how to set this up. Okay, so this is a third possibility, and among the three that we have seen, it is the only one which might involve a very small number of system calls in order to set up the communication. In the case of files, we have seen that for every read and write there would be a system call and huge disk I/O activities. In the case of using pipes, we have seen that every read or write would have to happen through a file descriptor, which might involve system calls. And the reason that I am worried about system calls is because whenever a system call occurs, remember that that is essentially a trap, and therefore it will involve saving the state of the process, the exception handling mechanism that we had seen at the end of the previous lecture. And therefore any IPC mechanism that involves a lot of system calls is not as good as an IPC mechanism that involves very few system calls. So among the three, the third seems to involve very few system calls. There may be the need for a system call to set up the shared region of memory, but subsequently the accesses to the variable x will happen using ordinary read and write operations. In other words, by including them, the variable x, in the right hand side of an expression or in the left hand side of an expression, depending on whether it is a read or a write. Therefore this is among the three the superior one that we from this perspective. Now there are other possibilities as far as IPC, inter-process communication, are concerned, and one which is akin to something that we have seen when we talked about human communication, we will talk about next. The idea that processes could communicate by sending and receiving something called messages to each other. So this is a completely new concept to us, communication by a process doing the activity of sending a message, and at the other end the message being received. So very clearly this is a new kind of a facility which the operating system has to provide, and we suspect that if the operating system does provide this kind of a facility, then there will be system calls or library functions which might be called send and receive, through which one process can package a piece of data within a message and send it to the other process. Okay. And similarly the other process can explicitly indicate that it wishes to receive the message which has been sent by the first process. So we have this idea of process P1 and process P2 communicating by explicitly sending these things called messages to each other. Okay, so with these four major ideas, we are going to see more about message sending and receiving later on. I am just introducing it as a possibility right now, and the actual kinds of facilities which might be available to do this we will talk about later. Now all four of these IPC mechanisms have the property that they can be used to communicate explicit data values. For example, I talked about how the current problem might be that I want to communicate the value 6 from process P1 to process P2. Now this kind of communication is not in general what may be required for all types of cooperation between processes. Okay. It is possible that sometimes processes may need to cooperate, but may not need to communicate explicit values. So in order to cooperate, they need not need to communicate explicit values. It might just something less than that may be all that is required for the cooperation to be facilitated. And let me just give you an example. One example is that the processes may not have to receive values from each other, they may just have to synchronize their activities. In other words, this is probably best illustrated through an example. The word synchronize is an important word here. Let me just give you a very, very simple, somewhat trivial little example. Let's suppose that the problem that I have is I have the need to multiply two matrices. Matrices are some form of large data structures, and let's suppose that the problem that I have is I want to multiply two such matrices, and since I now know about concurrent programming, I have decided that I will achieve this through a program that runs as three processes. Right? In my initial experiments with concurrent programming, I decided I would like to do this. So I decided to set things up so that first process P1 reads in the two matrices, then process P2 multiplies them, and process P3 writes out the result matrix to the output. I am going to assume that the matrices themselves are in a form of memory which is shared between the processes, such as using the shared memory we had talked about over here. Right? So I am not going to worry about the data within the matrices themselves. I am going to worry about the fact that if you think about this cooperation between these processes, the first thing that must happen is process P1 must read in the two matrices. After that, process P2 must multiply them. And it is important that process P2 does not start doing the multiplication before process P1 has finished reading in the two matrices. Think about it this way. Now, there's process P1, there's process P1, there's process P2, and there's process P3. And they have shared memory in which the matrices to be multiplied are available. So, process P1 is reading in the matrix, which is the first matrix which is to be multiplied, is reading in the second matrix which is to be multiplied. Now, what would happen if process P2 started doing the multiplication before process P1 finished reading in? It could be the case that process P1 has read in all of the first matrix to be multiplied, but has not finished reading in the second matrix to be multiplied, in which case the values within the second matrix could be garbage values. If you are lucky, they may be all zeros. So, if process P2 starts doing the multiplication on the data before all the data has arrived, then the result will be meaningless from the perspective of the task at hand. Therefore, it is important here that process P2 does not start doing the multiplication until process P1 has finished doing the reading of the matrices. Similarly, the job of process P3 is merely to write the result of the matrices. And clearly, process P3 should not start doing its work until process P2 has finished doing its work. Right? So, this is a situation where we actually need the processes to synchronize their activities. In other words, process P2 must not start until process P1 has finished reading the matrices, and process P3 must not start until process P2 has finished the multiplication. You notice that in this case, the processes P1, P2 and P3 are not sending values to each other. There is no need for them to communicate values between each other at all. There is no need for like the value 6 which had to go between the parent and the child in the previous case. Here that all that we have to ensure is that process P2 does not start until process P1 has finished, and that process P3 does not start until process P2 has finished its task. Now, this may look like a trivial example, since it is fairly clear that by setting up my concurrent program in this way, I may get no benefit in that process P1 will finish, and then process P2 will finish, and then process P3 will finish. And even if I had done all the activity in just process P1, it would have taken possibly the same or less time. But this was just an example of an extreme case of where I might set up a concurrent program, but very clearly an example where there is no need for data communication, but merely for the activities of processes to be synchronized with each other. Okay, so if this is the case, then there are likely to be IPC mechanisms, inter-process communication mechanisms, which do not have to handle the transfer of data, but merely have to handle synchronization. In other words, coordination between processes to make sure that one does not proceed beyond a certain point in its activity until one of the others has reached, let us say, a certain point in its activity. Right? In this particular example, we did not want process P2 to start its work until process P1 had finished its work, and so on. Right? So, this is what we refer to as process synchronization. The idea that one process, that the two processes P1 and P2 may have to be set up so that P2 waits for P1, or that they are synchronized with each other, not to proceed indefinitely until the synchronization had been achieved. Now, in practice, to do synchronization of this kind, some kind of mechanisms would have to be provided. Typically, they are provided by an operating system. Some of the mechanisms can be implemented by users using mechanisms that are available in user mode alone. But in general, people may talk about synchronization primitives. The word primitive is used to suggest that they are simple operations which are provided. They don't have to be implemented, but they are provided, and therefore they are referred to as primitives. Synchronization primitives, or primitive synchronization operations. And some of the names of some of these synchronization primitives are mutex, lock, semaphore, barrier. We will see each of these in a little bit more detail, some in this class, some in some of the classes to follow. So, just to recap, we are in a situation where we are talking about inter-process communication, in a situation where it is not necessary for explicit values to be communicated, but merely for synchronization between processes. So, that is the fifth possibility. Just to remind you, we have seen 4 others prior to this, and they all related to how explicit values could be communicated between processes. Now, moving right along, let us suppose that we are in a situation where the assumption is that processes that we have are communicating with each other and explicitly communicating values with each other using shared variables. this was the third of the options that we had in the list. The first was through files, the second was through pipes, the third was through shared variables, the fourth was through message passing, and the fifth was the mere idea of synchronization. So we're going back to the idea 3. We're going to spend a little bit of time talking about concurrent programming using shared variables. Right? So the idea is something like this. We've seen if there is let's suppose a 2-process program, and we look at a very simple example, because the objective of this slide is to illustrate a problem which arises, which we must be aware of if we want to do concurrent programming with shared variables. So let's suppose that we have a 2-process program, a program which is running as 2 processes, possibly parent and child, in which both the processes increment a shared variable. In other words, there's one shared variable called x, which happens to initially be 0, and what each of these processes does is to increment x, and I indicate that by the C x plus plus. So in addition to other things which they may be doing, so they may be doing other activity as well, but each of the processes is going to increment the shared variable x. Now when you look at this concurrent program, you will ask the question, what should be the final value of the variable x? And it should be clear in your mind that since x was initially 0, so this is the initial value of x, and x was incremented twice, we suspect that the final value of the shared variable x should be 2. We ask the question, what should the final value of the variable x be after this? And we suspect that the final value of the variable x should be 2, because one of these increments is going to change it from 0 to 1, the other increment is going to change it from 1 to 2. So we suspect that the final value should be 2. Right? However, there is a complication, and the complication arises from the following. You'll remember that when I say increments the variable using x plus plus, that is actually a little bit more complicated than just incrementing the variable if I think about something like the MIPS instruction set, because I know that x plus plus is really x equals x plus 1, and in order to do x equals x plus 1, the first thing that's going to happen is to load the value of the variable x into a register. So this might be the address of the variable x, the shared variable x. Subsequently, so I load it into the register R1. Subsequently, I increment register R1, and finally I update the variable x using the store word instruction. So this operation of incrementing the variable x is actually going to be in the MIPS. If the processor on which these 2 concurrent programs are running is a MIPS1 processor, then it's going to compile into this sequence of 3 instructions. Okay, now let's just see what could happen when these 2 processes end up running on that processor. Right, so I'm now formally describing this as a problem with using shared variables, so you must at this point anticipate that something is going to go wrong. But let me just point out right now that unfortunately the final value of the variable x could end up being 1. There's no guarantee that it's going to end up at 2. It could end up being 2, but on the other hand it could end up being 1. It can't end up being 0, but could end up being either 1 or 2. And this is not a good piece of news, because typically when you write a program that looks like this, your idea may have been that you wanted the variable x to end up at the variable 2. That's why you incremented it twice. But you're now told that if you wrote a concurrent program which runs as on a single processor using that kind of code, you may end up with the variable x having a value 1. And the way that this could happen is the following. It's possible that, well, we know that the sequence of events as described by that MIPS machine language instructions was that P1 loads x into R1 and then increments R1. It's possible that P2 then loads x into register before P1 stores the new value into the variable x, and the net result would then be that P1 stores the value 1 and P2 stores the value 1. Let me just outline this in a little bit more detail so that the consequence is clear. Okay, we'll come back to that slide shortly. Well, let me just maybe go through the slide in order, and then we'll come back to this particular example in more detail in a few seconds. Now, if this is the case, and as I said, we'll run through this in a little bit more detail shortly, this is a very dangerous situation, because we have to be careful in writing these kinds of concurrent programs. We must be aware that it may be necessary to synchronize the processes that are interacting using shared variables. And the problem seems to have arisen because process P1 and process P2 are sharing one processor, only one of them can be running at a time, and the operating system may switch from process P1 to process P2 somewhere in between the sequence of events that is going to happen. So if we are going to be using concurrent programming using shared variables, it may end up being necessary to synchronize the processes to avoid these kinds of wrong updates of shared variables. Okay, and the problem seems to arise, at least in this example, because I had two or more processes which were trying to update a shared variable. And therefore, we'll call parts of the concurrent programs where shared variables are accessed like this, we'll call them critical sections of the program. They are the important parts of the concurrent program which may have to be handled carefully, maybe using some kind of synchronization primitives, in order to cause the program to do what we think it's going to do. So in short, if we program using shared variables, then we have to treat the regions of the program which deal with the shared variables carefully, and hence we will refer to them as critical sections. Once again, this is in blue, suggesting that it's a commonly used technical term. Now, the problem which I talk about next is explicitly what has to be done in a critical section to ensure that the result of the concurrent program is what I may have thought. In other words, in this example, conceptually I thought that the result of incrementing x twice should be that x ends up at 2. Now, what is the problem with the critical section? The problem with the critical section was that I didn't seem to be properly synchronizing the activity of process P1 and process P2 in such a way that they could safely update the variable x. Now, in general, it may be the case that within these kinds of critical sections, the synchronization must be done so that the accesses to the shared variables are done one at a time. In other words, this notion of allowing one process to access the shared variable mutually exclusively of the other process. In other words, don't allow the two processes to actually be inside these critical sections during regions of time that the others are also in the critical section. And the name given for a synchronization primitive that can be used in such a scenario is to describe it as a mutex lock. Mutex is the abbreviation for mutual exclusion, and lock is the name for the mechanism, suggesting that it's going to ensure that the problem does not arise, the problem of strange values ending up in the shared variables. Now, the general idea behind how one could use a mutex lock is that the mutex lock, we can view it again as a data structure possibly provided by the operating system. The operations to this data structure are provided by the operating system. I'll describe the two operations on the mutex lock as acquire lock and release lock. And the general idea is that before entering a critical section, in other words, the regions of my concurrent program that are critical sections, I must put an acquire lock call before the critical section and a release lock call after the critical section, and that will in essence lock the critical section code to solve this problem and make sure that only one process is executing inside that piece of code at a time. Right, so the idea is that one will call acquire lock before the critical section, and it will provide some kind of a guarantee so that control will transfer back from acquire lock only when it is safe for the process to enter the critical section. And similarly, release lock will be called after the critical section and will allow another process to acquire the lock. This is the general mode of operation of the mutual exclusion primitive called the mutex lock. Okay, now let me just suggest how one could implement a lock, and this will give us a better understanding of the need for synchronization. So basically, I have to talk about the implementation of a function called acquire lock and the implementation of a function called release lock. So let's just do that. So I'll think of the lock, as I said, as being some kind of a data structure. So the acquire lock takes a lock as a parameter, release lock takes a lock as a parameter. These are not value parameters but reference parameters. Let's suppose that the lock variable is an integer variable, and initially it has the value 0. And the way that this implementation is going to work is that I'll initialize the lock to 0, and the meaning of the lock being 0 is that the lock is available. If the lock has a value of 1, that's going to mean that the lock is not available or the lock is in use. Right, so as far as using the lock is concerned, the lock initially has a value of 0, and we understood that the release lock operation was going to be used to make the lock available for the next process to acquire. And therefore, we suspect that all that has to happen in the release lock primitive is to set the lock variable to 0. This will make the lock available, which was, if you look back at the previous slide, that is what we wanted the release lock function to do. We wanted it to allow another process to acquire the lock, which means that it should make the lock available, and it will do so by setting the variable L to 0. Now what should the acquire lock primitive do? Basically it will be called before a process enters the critical section, and what it is supposed to do is it should return only when it is safe for the process to enter the critical section. In other words, it should return only when the value of the lock variable is 0, and also it should set the lock variable to 1, so to prevent other processes from entering the critical section. So in essence, what the acquire lock function primitive is going to have to do is, as long as L is equal to 1, in other words, as long as the lock is not available, it has to do nothing, it has to just wait. So what I am showing you over here is an example of a loop. As long as L is equal to 1, it has to loop, and therefore this loop just keeps executing while L equal to 1 until L becomes equal to 0. How can L become equal to 0? L can become equal to 0 because some other process executes set L equal to 0. Now after the acquire lock, the process which is executing acquire lock comes out of the while loop, that means that L is equal to 0, and then that process which wanted to acquire the lock can set L equal to 1, thereby preventing other processes from observing that the lock is available. And therefore this could be viewed as being an implementation of acquire lock. Remember, the objective of acquire lock was to keep a process which is trying to get the lock waiting until it is safe for the process to acquire the lock, and we understood that the lock is available if L equals to 0, which is why we kept waiting until L became 0. As soon as L became 0, we got out of the waiting loop and set L equal to 1, which informs other processes who may be checking that the lock is now in use. Now unfortunately, this is not a correct implementation, but before I come to that, this idea of looping, executing the checking on L equal to 1 repeatedly until L becomes equal to 0 is what I will refer to as busy waiting. Since it is a waiting loop, but it is a waiting loop in which some activity is happening, so the process which is executing this loop will be fetching and decoding and executing instructions. In other words, it will be keeping the processor busy, and which is why it is known as busy waiting. It is not a form of waiting where the operating system could say that this process is waiting, it is doing nothing, and therefore should be put into the waiting state. Rather, it is a kind of waiting in which the process is successfully executing instructions, but the instructions are such that it is just waiting for something to happen. Right? It is indefinitely checking, it is keeping on executing this check on the value of the variable L until L becomes equal to 0, and that will happen sooner or later when some other process releases the lock L, specifically if there is a preemptive scheduling policy. Now I had suggested that this does not work, and let me try to explain why this implementation fails. Now in understanding why this implementation fails, we will get a better understanding of the nature of the critical section problem itself. Now the implementation that we had for acquire lock looked like this. While L was equal to 1, we wanted to busy wait, so do nothing, and this is the busy wait loop. As soon as L becomes equal to 0, set L equal to 1. Now just like we looked at the increment of x in terms of the MIPS instructions that it might compile into, let us look at this piece of code in terms of the MIPS instructions that it might compile into. And what will end up is conceivably something like this. So I have a load word instruction. So the idea here is I am going to load the value of L into a register, then I am going to compare that with 0, and if it is not equal to 0, I loop. So the loop that you see over here is the loop above. The instructions that you see before are setting R1 equal to 1 and then storing that value into the lock variable. So this is the L equal to 1. So the first two MIPS instructions relate to the busy wait loop, and the second two MIPS instructions relate to setting L equal to 1. So this looks like a reasonable way to implement, this looks like a reasonable compilation of the sequence of the C code that we see on the left. Okay, now the situation that we are in is, let me just get out of this particular markup. Okay, the situation that we are in is we have this piece of code, and we understand that this is what is going to happen when a process executes the acquire lock function, and we need no longer worry about the C instructions on the left. So, I will get rid of the C instructions on the left, and let us suppose that there are two processes, process P1 and P2. Sorry, let me assume that the lock is currently available, in other words L is equal to 0, and that there are two processes P1 and P2 which are trying to acquire the lock. Right? So, there are two processes which want to acquire the lock because both of them want to access a shared variable. So, I am going to show you timelines for process P1 and P2. I am going to draw the timelines vertically because I am going to mark the timelines with instructions that are being executed. So, let us suppose that currently process P1 is executing, and therefore it starts by executing the first instruction of this, it is executing in the acquire lock function, and it executes the first instruction. So, it loads the value of the lock into the register R1. So, it gets R1 equals 0. Let us suppose that at this point in time there is a context switch. Now, remember that the operating system at the end of the time slice of a process will switch from that process to another process, one of the other ready processes. Now, it is quite possible that a context switch could happen after process P1 has executed this first instruction. So, this is a perfectly legitimate possibility. Let us suppose that the operating system now makes process P2 the running process. Process P1 has been put into the ready queue. Process P2 also is executing this sequence of instructions. Let us suppose that it successfully executes all the 4 instructions. What it is going to find out is that it will read into its register R1 the value L equal to 0, just like process P1 did. Note that process P1 had read the value of L equal to 0, but did not go to the subsequent statements and modify the value of L. Consequently, when process P2 started executing, it too reads the value of L equal to 0, but goes ahead and modifies the value of L, and therefore enters its critical section. So, process P2 has successfully acquired the lock and is executing in its critical section. Let us suppose that at this point in time process P2 suffers a context switch, and that process P2 becomes a ready process and process P1 becomes a running process. Now, when process P1 resumes its execution, it will be at a point where its PC value will be such that it will execute the branch if not equal to 0 instruction. So, it does that. In fact, it goes from the branch if not equal to 0, it checks the value of R1. As far as it is concerned, R1 is equal to 0 because it has successfully loaded R1 with the value of L at that point in time, and therefore it too successfully executes these instructions and enters the critical section. So, we are now in a situation where you see that this implementation can allow two processes to be executing in the critical section at the same time, and therefore it does not provide the kind of guarantees that we were looking for. This in fact gives us some idea of why the earlier example that we had seen was also a hazardous example. Let me just go back to the earlier example. So, we had a situation where process P1 and process P2 are both executing this piece of code, and let us suppose that process P1 executes initially x is equal to 0, process P1 executes load word, so that as far as it is concerned its register R1 contains the value 0. Let us suppose that at that point in time there is a context switch and process P2 starts executing. So, process P2 also loads from the variable x, which still contains the value 0. So, it loads the value 0 into R1. It increments its R1 by 1 to make R1 equal to 1. It stores the value of R1 into the variable x, so that x becomes equal to 1. Let us suppose that at this point in time there is a context switch back to process P1. P1 is at a point where it has a value of 0 in its register R1. It increments R1 by 1 to come up with the value of R1 equal to 1, and it stores this value of R1 into the variable x, overwriting the value 1 which was written there by process P2 with a new value 1, which is how it was possible for two processes to increment the variable x, but still end up with a situation where the value of the variable x was only 1 and not 2. Now, this was the problem with the variable x, and that was the reason that we wanted to have a solution to the problem in the form of an operating system support such as a lock, and we defined the idea of the critical section. But in doing so, apparently we came up with an implementation that was inadequate. This particular implementation is inadequate, and if we look at this implementation we realize why. We realize that in this implementation, this itself is a critical section. This is a region of code where if there is a context switch in between, the consequences can be that the overall effect is not what we would have wanted, and that by trying to implement an operating system primitive in which there is a source of problems in itself, we are not solving any problem at all. Consequently, very clearly, we need to have solutions or implementations of things like the lock which go beyond this seemingly correct interpretation of how to safely make a lock available, and possibly requiring hardware support to do the same. When we continue in the next lecture, we will look at a specific implementation which requires hardware support in order to implement a mutex lock, but is correct and can therefore be used as the basis for writing programs, concurrent programs, which use shared variables in order to facilitate the communication and therefore the cooperation of multiple processes in working towards a common objective. Thank you.